Welcome to the next video in this series of short introductory videos on chemical relationships. In previous videos, linked in the description below, we saw how reactions occurred in the solid state, where one could measure mass, but where it was vital to use the molecular weight to turn that into the number of moles or the number of atoms or molecules present in order to complete the relationship. In this video, we'll look at a special type of reactions called aqueous reactions. Aqueous reactions occur in water. You will see that this is important because obviously water is the thing that everybody looks for when one is looking for life. There are three types of aqueous reactions. You have precipitation reactions, acid-base reactions, and oxidation-reduction reactions. Each of these will be gone into in some detail and explained in the following few minutes. It's also important or useful to realize that the last two, acid-base reactions and oxidation reactions, are essentially the basis of life. They are the reactions that occur in digestion and metabolism that provide energy. So, fundamentally, aqueous reactions occur in solution. A solution is a homogeneous mixture composed of two parts. You have the solvent, which in case of aqueous reactions is water. Very simply, the solvent is the majority component. The solute, which in this case would be the reagents, is the minority component. What differentiates aqueous reactions from reactions in the solid phase is that the amount of solute is a variable. This is called the concentration of the solute and is usually denoted by square brackets. Once again, one winds up measuring this with a ratio. The ratio in this case is called molarity, symbolized by a capital M. This is the ratio of the number of moles of solute to the liters of total solution. So using molarity, one has a question. How many grams of sodium hydroxide are required to prepare 150 milliliters of a 0.85 m solution? 0.85 m means I have 0.85 moles of sodium hydroxide per liter. It's always important in everything in life to be careful, and in the case of chemistry, you have to mind the units and the scale. Molarity is moles per liter. However, I have volume given in milliliters. So first of all, multiplying by 150 milliliters is 0.15 liters. One is multiplying because moles per liter times liters cancels the liters and gives 0.128 moles of sodium hydroxide. One sodium, one oxygen, and one hydrogen are going to weigh 40 grams per 1 mole. And again, one multiplies to make sure that the moles cancel. So the answer would be this solution would contain 5.10 grams of sodium hydroxide. So this is how one uses the concept of molarity to turn a variable solution, once again, into the number of moles which are needed for a reaction. Moving on to the specifics of the reactions themselves. One starts with precipitation reaction. Precipitation reactions are easily understood if one memorizes some simple rules. Those rules are based upon common anions: nitrates, chloride ions, sulfates, sulfides, hydroxides, and carbonates. The rules simply state what is soluble and what is insoluble. The simplest rule is the rule for nitrates. All nitrates will dissolve in water. Chlorides are also highly soluble, with 3 exceptions. silver, lead, and the mercuric Hg2 2+ ions with chloride ion are all insoluble. Similarly, sulfates are generally soluble, with the exception of strontium, barium, and lead 2+ ions. Moving on, sulfides are generally insoluble, with the exception of group 1 +1 ions, group 2 +2 ions, and the ammonium ions. Hydroxides are also generally insoluble, with the exception of group 1, strontium and barium ions, and again the ammonium. Carbonates are almost exclusively insoluble, with the exception of lithium ion and ammonium carbonate. So, if one memorizes these simple rules and notes a trend, the trend being that the first three, nitrates, chlorides, and sulfates, are mostly soluble, with some exceptions. The following three common anions are mostly insoluble, with some exceptions. If one knows the rules and knows the exceptions, one can easily use them. For example, a question. I mix a solution of lead-2 nitrate with ammonium hydroxide. How can I tell if a precipitate will form? First of all, one has to note what ions are going to be present. If lead nitrate dissolves, I'd get lead-2+ and 2 nitrate ions. Sodium hydroxide will generate an Na+ and an OH-. I now have 4 ions, 2 cations, 2 anions. The next step, identify all the possible combinations. My 2 cations are lead-2+ and sodium +1. My 2 anions are the nitrate ion and the hydroxide ion. 2 positives and 2 negatives can make 4 possible combinations. Positives will only be attracted to negatives. You'll never get a compound with a positive and a positive, or a negative and a negative. So if I look at this, the lead could be attracting the nitrate in a ratio of 2:1 to give me PbNO3 2. The lead could be attracted to the sodium could be attracted to the nitrate, 1:1 NaNO3. The sodium can be attracted to the negative hydroxide to give me NaOH. Or in a 2:1 ratio, the lead ion can be attracted to a hydroxide to give me PbOH2. One then goes back to apply the rules. The first case is the simplest case. The easiest rule to remember is all nitrates are soluble. So PbNO3 and NaNO3 are both soluble and will not precipitate. The rule for hydroxides, however, states that they are generally insoluble except for group 1, strontium, and barium 2+. So since sodium is in group 1, sodium hydroxide will dissolve. However, lead is not one of the exceptions, so lead-2 hydroxide will not dissolve, and the answer is, therefore, yes, I will get a precipitate. That precipitate will be lead-2 hydroxide. One can then go further with this example, where one could ask for the net ionic equation. Very simply, the net ionic equation is the balanced equation for the precipitate. We've already determined that lead-2 hydroxide precipitated, and therefore you have a very simple question. What things do you need to make lead hydroxide? One needs lead-2+ and 2 OH- to make 1 PbOH2. One will notice that we started out with 4 ions. 2 of them precipitated. The other 2 are what are called spectator ions. Essentially, like in a sporting event, a spectator just sits and watches. In this case, the sodium and the nitrate ions remained in solution. They did not participate, so they simply spectated. This is how one handles precipitation reactions. The key is to know and be able to use the rules of solubility. Next, one has acid-base reactions. The knowledge of acids and bases had been around for literally eons. A scientist named Svante Arrhenius was the first one to quantify it. It had been known that acids turned blue litmus to red, and bases turned red litmus to blue. Arrhenius noted that the things that turned blue litmus red all had H plus ions, so he defined an acid as something that donates H plus. He also noted the things that turned red litmus blue all contained hydroxide ions. So those were the bases, anything that donated an OH minus. This is the fundamental definition of an acid and base. An acid is any species which donates H plus, and a base donates OH minus to solution. Arrhenius also noted that not everything dissolved completely. Some things did dissolve completely, and he called those strong electrolytes. A strong electrolyte is anything that dissociates 100% in solution. Another thing coming up that's important to know is that these are also rare. There are only 6 strong acids. The strong acids are HCl, HBr, hydrogen iodide, nitric acid, perchloric acid, and sulfuric acid. Those are the only H plus donating species that will dissolve 100% in solution. Additionally, there are only 7 strong bases: lithium, sodium, potassium, rubidium, and cesium hydroxide, the group 1 hydroxides, plus strontium hydroxide and barium hydroxide. You will note, bringing things together, that the strong bases also constitute all of the soluble hydroxides. So Arrhenius noticed that few things dissolved completely, other things only partially dissolved. These he called weak electrolytes. And he noted, or he hypothesized rather, that instead of dissolving completely, these are going to exist in equilibrium in solution. For the present, for an introduction, one does not have to worry about weak electrolytes. They will be gone into later on as one goes further into chemistry. The acid-base reactions that we'll be looking at will be between strong acids and strong bases. So if one looks at the reaction of a strong acid plus a strong base, for example, from the list, HCl reacting with sodium hydroxide. They are both considered strong because they dissolve completely in water. So HCl will dissolve to give an H plus and a Cl minus. Sodium hydroxide will dissolve completely to give an Na plus and an OH minus. These 4 ions can recombine. H plus and OH minus obviously give water, which leaves us with Na plus and Cl minus. Common table salt, sodium chloride. However, from the rules of solubility, sodium is one of the soluble chlorides. Therefore, it will remain in solution. Since the ions occur on both sides of the balanced equation, the sodium ions cancel and the chloride ions cancel. So for any reaction of a strong acid donating H plus and a strong base donating OH minus, the balanced equation will always produce, very simply, water. This is called the neutralization reaction. As an example, a question: how many milliliters of a 0.15 m HCl solution are needed to completely react with 20 milliliters of a 0.2 m sodium hydroxide. Bringing things together, the capital M means I have 0.2 moles of sodium hydroxide per liter. 20 milliliters is 0.02 liters. That gives 0.004 moles of sodium hydroxide. The sodium hydroxide is my base. Sodium is a spectator ion, and the sodium hydroxide donates 1 OH minus, which means I have 0.004 moles of OH minus in solution. The neutralization reaction says I need 1 H plus for every 1 OH minus, and my 0.004 moles of H plus are coming from HCl, which has 1 H plus. Therefore, to completely react with 20 milliliters of a 0.2 mole of sodium hydroxide solution, I would need 0.004 moles of HCl at 0.15 moles per liter. That would give me 0.267 liters, or 26.7 milliliters. So, in summary, acid-base reactions, for now, can either be between strong or weak. The differences between those are in a further video that's linked in the description below. But at present, worrying about strong acids and strong bases, one simply makes water, since the acid donates H+, the base donates OH- in the neutralization reaction. That is the sum total of strong acid and strong base chemistry. The third aqueous reaction is called redox, short for oxidation and reduction. Oxidation is defined by the loss of electrons. Reduction is defined as the gain of electrons, perhaps the easiest to remember since an electron has a negative charge. So if you're adding negatives, the charge is going down or being reduced. The key point for these oxidation or reduction reactions is that it's an exchange. The number of electrons lost has to equal the number of electrons gained. That means when one is looking at a redox reaction, one has to balance both mass and charge. For example, qualitatively, chromium reacts with chlorine to give chromium 3+ and chloride ion, Cl-. One knows that this is a redox reaction because the charge is changing from left to right. However, one has to have a system in order to balance this by breaking it down into small, manageable chunks. The easiest thing to do is very simply do first, split the reaction in half. One can just read that chromium goes to chromium 3+, and chlorine goes to Cl-. Once the reactions are separated, one goes back to balance the mass. I have 1 Cr going to 1 Cr3+. That's balanced. However, a Cl2 going to 1 Cl- is not balanced. So Cl2 should go to 2 Cl-. Once one balances the mass, one moves back to balance the charge. Separating the reactions like this makes it easier to determine oxidation and reduction. For example, chromium is going up to chromium 3+. In order to do that, it had to have lost 3 electrons, which means chromium was oxidized. If chromium is oxidized, Cl2 going to 2 Cl- has to be reduced. In this case, each chlorine picked up 1 electron. I have 2 chlorines to get to 2 chlorides. So Cl2 will pick up 2 electrons in the reduction to give 2 Cl-. The fourth step is to simply put everything back together. Once again, electrons lost have to equal electrons gained. My oxidation was by 3 electrons, and my reduction was by 2. The lowest common multiple of 2 and 3 is 6. Therefore, I need 2 chromiums going to 2Cr3 plus 6 electrons will balance with 3 times the reduction reaction, 3Cl2 plus 6 electrons going to 6Cl minus. My 6 electrons are now balanced, 6 on the left, 6 on the right, and they will cancel. And my overall balanced equation is now going to be 2 moles of chromium plus 3 moles of Cl2 going to 2 moles of Cr3 plus and 6 moles of chloride ions. Looking at another, more complicated example to reinforce how valuable it is to have a system. I have here the reaction of iron 2 plus and a permanganate ion to go to iron 3 plus and Mn2 plus. Once again, if I am looking at this reaction for the first time, I'm going to note 2 changes to 3, -1 changes to +2. The oxidation states, or the charges, are changing, so I know I am looking at a redox reaction. I then apply the system. I split the reactions in half, with iron 2 going to iron 3, and permanganate, MnO4 minus, going to Mn2 plus. I now deal with each of those half reactions in turn by balancing the mass. Once again, I have 1 iron 2 plus going to 1 iron 3 plus. That's balanced. My permanganate, MnO4 minus, is going to Mn2 plus. You will notice that this is not balanced because I am missing 4 oxygens. At this point, one remembers that one is dealing with aqueous solutions. If one needs oxygen, one will get it from water. So since I need 4 oxygens on the right, that means I will have to add 4 waters. By adding 4 waters, I also added 8 H pluses. So, in water, MnO4 minus plus 8 moles of H plus would go to Mn2 plus 4 H2O in order for the masses to cancel. After the masses are balanced, one goes back to balance the charge. And in this case, one sees why it is important and why it is useful to split the reaction in half. Very simply, Fe2 plus going to Fe3 plus is obviously going up by 1. It is losing 1 electron, so that means it is being oxidized. Once one determines which half reaction is being oxidized, it's easy to determine which half reaction is being reduced. In this case, if iron 2 plus is being oxidized, the permanganate has to be reduced. At this point, I have 4 elements. A remembering of the basic understanding of the periodic table. Which elements are being oxidized and reduced? My first element present is oxygen. Oxygen in group 6 on the periodic table always forms an ion with a charge of -2. That's not going to change. Hydrogen in group 1 on the periodic table always is going to have a charge of +1, which will not change. Therefore, if oxygen isn't changing and hydrogen isn't changing, the manganese has to be changing. On the right, the manganese has a charge of +2. On the left, I have a permanganate. In the permanganate, MnO4 -1, I have 4 oxygens. Each oxygen has a charge of -2, which means the 4 oxygens add up to -8. The entire molecule has a charge of -1. So the question, what -8 gives you a -1, tells you that the manganese on the left is a +7. Going to a +2 means the reduction was by 5 electrons. To recombine this, once again, the lowest common multiple of 1 and 5 is going to be 5. So I'll need 5 ion 2 going to 5 ion 3 with 5 electrons to balance a permanganate with 8 H pluses and gaining 5 electrons. The 5 electrons cancel, left and right, and I am left with a balanced equation of MnO4 plus 8H plus 5 ion 2 going to Mn2 plus 5 ion 3 and 4 water. One note to make on this particular reaction, since it is an aqueous reaction, and we used water to get the O minuses, I also picked up H plus, which means this reaction is occurring in acid, since acids donate H plus. One could be asked to balance this reaction in base. To balance in base, one very simply neutralizes the acid. I have 8 moles of acid, 8 moles of H plus. To neutralize that, I need 8 moles of base, OH minus. To keep things balanced, whatever I add to the left, I also have to add to the right. So, I will wind up with a permanganate and 8 waters, 5 ion 2, going to Mn2 plus, ion 3, 4 waters, and 8 OH minuses. Doing some bookkeeping, I notice water is showing up on the left and the right. I got 4 on the right, 8 on the left, meaning when everything is completely balanced, I will have a permanganate with 4 remaining waters reacting with 5 Fe2 plus to give Mn2 plus, 5 ion 3, and 8 hydroxides in base. So this concludes the discussion of aqueous reactions. Again, reactions that occur in water are very important for life. They are precipitation, where you have to know the rules of precipitation. Acid-base, which in the case of strong acids and strong bases produces water by neutralization. And the exchange of electrons in oxidation and reduction. This concludes the discussion of reactions that occur as solids and in solutions. The following videos, linked in the description below, will look at gas phase reactions. Thank you very much, and I hope you found this interesting and useful.